Alright, hello everyone. Today we're going to be talking about the strong nuclear force, and we'll have a look at proton repulsion a little bit as well. So the nucleus contains multiple positively charged protons packed into an incredibly small space. So why doesn't it just fly apart? So within the nucleus, we have these protons and neutrons sitting around each other, very densely packed. And then you obviously have the electrons orbiting around the nucleus as well. This is a very simplified diagram, but it's the general idea. So the protons carry a positive electric charge. So from Coulomb's law, we know that like charges repel, and the electrostatic repulsion between two charges increases as the distance between them decreases. So you would think the protons that are positively charged and are very close together would repel each other. Like inside the nucleus, protons are separated by distances on the order of 10 to the negative 15 meters, which is femtometers. They're extraordinarily small separations. The electrostatic repulsion between protons is enormous. Okay. So gravity also acts between the protons as well, but at this scale, gravitational attraction is many orders of magnitude. It's too weak to counteract that electrostatic repulsion. So a different force entirely is responsible for holding the nucleus together. So the strong nuclear force is the force that binds protons and neutrons, which are called nucleons. It binds them together within the nucleus. It is the strongest of the four fundamental forces. So unlike the electrostatic force, the strong nuclear force is attractive between all nucleons, protons and neutrons alike, regardless of charge. So a strong nuclear force holds those nucleons together. So critically, the strong nuclear force is extremely short range. It only operates over distances comparable to the size of a nucleus, approximately 1 to 3 femtometers. Beyond this range, it drops off rapidly to 0. So the range is only 1 to 3 femtometers. Now, a very short range, so if we're looking even smaller now, at about 0.5 femtometers, the strong nuclear force becomes repulsive. So if it's less than 0.5, repulsive. So the strong nuclear force becomes repulsive, prevents the nucleons from collapsing into each other. Between approximately 0.5 and 3 femtometers, it is attractive, holding it together against electrostatic repulsion. The stability of a nucleus depends on the balance between the attractive strong nuclear force and the repulsive electrostatic force between protons. This is why larger nuclei require increasing number of neutrons. Additional neutrons contribute strong nuclear force attraction without adding to electrostatic repulsion, as neutrons have a neutral charge. So to summarize, protons repel each other through the electrostatic force. At nuclear distances, this repulsion is enormous. The strong nuclear force is the attractive force that binds all nucleons together, overcoming this repulsion. It is the strongest fundamental force, but it operates only over extremely short distances, approximately 1 to 3 femtometers. Nuclear stability depends on the balance between these two forces. Follow for daily QCAA content.